A thesis of solar panels, inefficiencies, engineering problems, and environmental hazards. This paper is in response to an article in the Kentucky Living magazine discussing potential grid solar power projects. The article stated 3 facts from which I will deduce as to the potential problems. The 3 facts are: 1. The promise of 160 megawatts or million watts of power. 2. The facilities will cover 1,700 acres, 8,228,000 yards, or 6,879,655.918 meters squared. And 3. The power agreements are 20-plus year contracts. 2 assumptions will be made in this paper's calculations. Those assumptions are that the solar constant for visible light is equal to 640.4 watts per meter squared, or 1.2 yards squared, and that the solar constant for infrared light is equal to 606.8 watts squared. To start with the power output, I took the stated 160 megawatts of power and divided it by the meters of the facility, and came to the number of 23.26 watts per meter squared. To check this number, I multiplied it by the stated square meters of this facility and came up with the number of 160,020,796.7 watts. I determined that the inconsistencies came from the assumption that in the equation that all 1,700 acres were producing power. So to correct for this, I subtracted the 20,796.7 watts over the stated 160 megawatts and divided that by the earlier number of 23.26 watts per meter squared and deduced that 894.9097 meters squared, or just over 10,000 yards, were not producing power. But going back to the number of 23.26 watts per meter squared, taking it and dividing it by the solar constant of visible light, 640.4 watts per meter squared, which equaled 0.0363 or 3.63%. Now this 3.63% efficiency seemed entirely too low. After a few phone calls, I have yet to determine if this number is net or gross. Personally, I believe it to be net. As the paper stated, it is a 20-year contract, and solar panels that inefficient would be unlikely to live a quarter of that time. And the list of electrical losses due to heat will start to add up to the losses I could think of are as follows. Solar panels only converting about 22% of the visible light into electricity, not considering for collector solar cells, with the rest being reflected back through the atmosphere or converted to heat. Charging and discharging storage batteries. Assumption that the solar array will have storage batteries. An inverter to convert the panels or batteries direct current electricity into alternating current AC electricity for transmission to the grid. Unconfirmed the phase of the AC. A step-up transformer to lower current losses by increasing the voltage transmission losses, for which the best is about 6.9 to 7% power loss due to heating. Step-down transformers at the location, the place where the power is being sent to, substations, and the pole transformers for the residential use, not stated in the article. This is a long chain of losses that I believe are the causes for the 3.6% of the solar constant of visible light. Next part of this paper will be addressing the potential engineering and environmental problems that could arise, starting with the engineering problems. Solar panels work best in cool weather and in direct sunlight. And as most people are aware, the sun moves from east to west. So the solar panels also must move if peak efficiencies are to be achieved. The movement of the panels will depend on electric motors and a cooling system, and a control system, either light sensors or GPS tracking, along with the potential for annual shifts of the sun from the north to the south. Solar panels like to be in cool weather. The hotter a solar panel becomes, the more repeatedly it happens, the more likely it is for the panel to be damaged. I have no hypothesis on how this would be solved. The panels in wind will produce drag or lift on the panels, thus the frames would need to be able to handle the stresses and require a concrete foundation of unknown depth. More on this concrete foundation in the coming environmental section of this paper. To ground physically them, environmental problems could start with the manufacturing of the panels, frames, wiring, etc. or the transportation of the finished products and the installation of all of it, which requires fossil fuels and in some may generate toxic chemicals. This is unfounded. But this paper will not go into the area. It will... Instead, this paper will assume the facility, if built and operational. After calling the manufacturing companies and receiving unsatisfactory answers as to the composition and types of the solar panels that could be used, I will name a few types of the solar panel composition, starting with least toxic, better efficiencies, and most expensive. As the list goes down, toxicity will go up and efficiencies and cost will go down. Gallium arsenide, silicon boron, arsenic, selenium. Unknown if selenium and silicon and element pair or two pairs of silicon plus element. Selenium sulfide, cadmium sulfide. Table 1 is a list of arsenic compounds, selenium compounds, and cadmium compounds toxicity in milligrams per cubic meter or ounces in cubic yards. Arsenic compounds, anything greater than 5 milligrams or 0.0018 of an ounce is directly lethal to humans. Selenium, 0.001 of a gram or 0.000353 of an ounce is dangerous to humans. Cadmium compounds, 0.0005 grams or 0.000176 of an ounce. The chances... Now this comparison is a tad unfair and unrealistic, as the chances of these compounds becoming powder and airborne are slim, but the possibility of a panel being broken in, say, strong winds or hail, yes, this facility is being planned for a tornado/hail-prone area, is much more likely to happen than what would the procedures be for the prevention, the containment, or cleanup to prevent toxic elements from entering into the waterways or into nearby soil. The next part is a bit finicky, as I am unsure I did the equation right. The equation in question is the change of T is equal to Q divided by M times the specific heat capacity. I attempted to use it to calculate the change in temperature, delta T, where Q is equal to the solar constant of infrared light, 606.8 watts per meter squared, minus concrete's reflectiveness, which is about 10 to 50% for this calculation, divided by the mass, which is equal to 2.7 grams per cubic centimeter, times the specific heat capacity, which is 2.21. And I limited the area to the 894.097 meters squared, or 10,069.33 yards squared, that were not producing power with a 30 centimeter or 1 foot depth, which comes out to 242.19 kilograms of concrete for M and 303.4 watts per meter squared, times that by the total square meterage, the 894.097 meters squared, to equal a change of 178.37 C or 353.006 Fahrenheit. This calculation does not take into account the poor thermal conductivity of concrete. And that's that.
Now, people might make the assumption that you are totally against solar panels. What is your stance on solar panels?
Solar panels would be great, but our technology is not there. It needs a lot more work.
Is it better per household, more efficient per household, less dangerous per household?
I would say for a household it would be more dangerous, but there's also the problem of cleanup as well, since some of these cheaper panels do use toxic elements. It's kind of like having a mercury bulb. You do have to get rid of the mercury, you can't just throw it in the backyard. You just can't. So, per household, I'd say solar panels are far more efficient at producing power, especially if you want to cut down your electric bill, but for grid power, which needs to be reliable, it's just not practical. I mean, just right now, we've had almost no sun for 2 days. That type of weather inconsistency just can't be allowed for power generation. So you might as well just stick with your coal. That's my opinion. Or better yet, go to something like nuclear. At least that dangerous stuff decays eventually and is contained.
Why do you think so many people are afraid of nuclear?
Probably due to the fact that you can't see it. The other problems that come with it is that it just sticks around for so bloody long.
Well, we can't see electricity either, and a lot of people aren't aware that coal generates electricity.
I guess they fear that the radiation is going to microwave them or something.
And yet we use microwaves to heat up our food.
Yeah, potentially it's a fear of another Chernobyl, but then again, Chernobyl was the result of Soviet needs to test. They purposely they purposely forced it into a failure to see how it would work, and their emergency systems failed.
So do you think these fears are unfounded?
Not unfounded, just blown way out of proportion. It's kind of like fearing you're going to get bit by a rabid bat while you live in the Arctic. It's just not likely to happen. I'm not saying a bat couldn't get there, but the chances are the bat's going to die before it happens.
Got it.
For that analogy.
Okay, so if anybody has any comments or can assist with this, go ahead and leave us a comment.
Yep.
And thank you for visiting. If you didn't understand a lot of it, welcome to the party.
This is Booksauce. Thank you for watching.